urgent, precise. In software engineering, a single localized error can trigger a violent cascade that brings down an entire application. This is the ripple effect. This extreme fragility is the hallmark of a monolithic architecture. When every function in a codebase is deeply intertwined with every other function, a localized error cannot be quarantined. The system acts as a single, highly reactive organism, where a failure in one obscure feature crashes the entire machine. To engineer resilience, we transform this chaotic mass into a partitioned network. This structural countermeasure is called functional independence. It's a measurable state of stability, achieved through deliberate design choices dictating how code is organized and communicates. This stability is governed by two opposing structural vectors. First, the internal focus of a given module, known as cohesion. Second, the external interdependence between different modules, known as coupling. Balancing these two vectors is the primary defense against the ripple effect. It allows engineers to build systems that scale gracefully and remain intellectually manageable for human teams. To understand how to achieve this balance, we look at the absolute smallest building block of the system, a single software component, represented here as an object-oriented class. Inside, it contains methods, which execute logic, and attributes, which store data. When a developer assigns too many responsibilities to this single block, it becomes a schizophrenic component. It attempts to parse data, format text, and write to a database all at the exact same time. This lack of focus creates a structural hazard. When multiple unrelated behaviors share the same physical space in the code, isolating a bug or writing a test for a single feature becomes virtually impossible. The engineering ideal is single-mindedness. A highly optimized component should do exactly one thing, and it should contain only the methods and data required to execute that specific task. We define this internal, single-minded focus as cohesion. Before a module can safely interact with a massive system, its internal boundaries and purpose must be structurally flawless. Cohesion exists on a qualitative spectrum, ranging from fragmented chaos at the bottom to highly focused utility at the top. The gold standard is functional cohesion. A component performs one targeted computation using its own internal data, returning a clean result. Compare that to a fragmented class. Multiple methods execute logic without sharing data. The class acts as an artificial boundary, trapping distinct entities. Engineers cannot rely on gut feeling or visual inspection to spot this fragmentation in a codebase of 1 million lines. They must quantify it mathematically. We measure this using LCOM, lack of cohesion in methods. It tallies method pairs operating without sharing data. The higher the count of isolated methods, the higher the score. A high score indicates dangerous complexity. The ultimate objective is driving LCOM towards 0, ensuring absolute focus. Securing a component from collapsing inward is only half the equation. Perfect internal cohesion is useless if it cannot safely communicate with the outside world. We pivot now to external communication pathways. Coupling is the qualitative measure of how strongly different classes are connected. As interconnecting lines increase, complexity scales aggressively. Susceptibility to the ripple effect skyrockets because one change dictates a change in dozens of others. The most dangerous dependency is content coupling. This occurs when one component bypasses standard protocols and forcibly manipulates the internal data of another. It violates information hiding, allowing unseen side effects to propagate without warning. We contrast this with acceptable data coupling, where components communicate solely by passing specific, required arguments through properly defined interfaces. To track external threats, we use the CBO metric, coupling between object classes. It counts the exact number of unique external classes a module is tethered to. A high CBO score means the class is incredibly fragile and nearly impossible to isolate for testing. To suppress CBO, engineers apply the law of Demeter. This acts as a strict constraint, dictating that a method only talks to its immediate neighbors. If cohesion dictates the strength of the individual brick, coupling dictates the structural integrity of the mortar, holding the entire system together. With these mathematical rules established, we return to the macro view of the monolithic architecture. Engineers actively untangle this web through a process called refactoring. This requires breaking large, fragmented nodes into smaller, distinct units. By isolating unrelated behaviors, this process explicitly lowers the LCOM score. Internal cohesion increases. Simultaneously, the chaotic web of interconnecting lines is pruned down to only the most essential, strict data pathways. By enforcing the law of Demeter, external dependencies are limited, the CBO metric drops, and overall coupling is minimized. You cannot drive coupling to absolute zero. A system with zero external dependencies is a system that cannot process input or deliver output. Software design is an endless act of optimization. Maximize cohesion while minimizing coupling. When we apply these metrics, we secure the operational reality of the system. An error in a highly organized modular network is safely quarantined. This independent architecture prevents developers from destroying each other's work. By isolating concerns, a team can modify a payment gateway without accidentally crashing the user authentication database. Mathematical modularity ensures that highly distributed, global teams can write, merge, and deploy code in parallel safely. It also provides a massive testing advantage. Components with a low CBO score can be validated completely in isolation, eliminating the need to spin up massive scintillated network environments just to verify a single feature. The ripple effect guarantees that bad architecture will eventually collapse under its own weight. True system scalability is achieved by adding code that structurally cannot break the rest of the machine. A software empire survives not by the brilliance of its individual functions, but by the mathematical rigor and absolute independence of its boundaries.